Greetings. In this video we are going to discuss a small theorem related to circles and triangles. To be more precise, related to a circumcenter, the incenter and an angle bisector. Consider a triangle with a circle drawn. So I am drawing the circle first because it is easier to draw a triangle on top of a circle than to draw a circle on top of a triangle. So assume that we have a certain triangle and we have drawn the circumcircle of this triangle. Let me name the vertices. Let it be called A, let this be B, and let this be C. Now let me draw or point the incenter of triangle ABC. So I am not going to draw the actual circle and figure out the incenter. Let me just draw a rough. So this looks like a incenter to this triangle. So this is the incenter of triangle I. Now if I draw a ray passing through point A and the incenter I, then I'm sorry. Why is this happening? Okay, alright. So if I draw a ray passing through point A and the incenter I, then it will cut the circumcircle at a certain point, this point. Let this point be called D. The ray passing through A and I will cut the circumcircle at point D, and the theorem that we are talking about says that there exists a circle with center at point D and passing through points B, I, and C. So this is the theorem for any triangle. Now let us discuss the proof of this theorem or lemma, whatever one would like to call it. It would be sufficient to prove that dB is equal to di, and further both dB and di is equal to dc. It will be sufficient to prove this, which will conclude the theorem, the proof of the theorem. So let me show that dB is indeed equal to di in the following manner. Let me draw first of all, let me draw a segment passing through B and connecting. Let me connect a segment through from B to I, and we notice that angle IBC is equal to, alright, just a moment, I have to connect two more points, B and D. Alright, angle IBD is equal to angle IBC plus angle CBD. This is what we notice from the diagram. Now angle IBC is half angle B, where angle B is ABC, angle ABC. Angle B is nothing but angle ABC. Angle IBC is equal to half angle B, because I is the incenter, therefore BI is the bisector, of angle angle B. So angle IBC is half angle B, because BI bisects angle B, as I is the incenter. Further, we notice that angle CBD is equal to angle CAD. Angles subtending the same arc are equal. And further, we notice that angle CAD is half angle A, where angle A is angle BAC basically. Again the same reason, I is the incenter and AI bisects angle I. So CAD, angle CAD is half of angle A. So let me make some space here. Now, so from this equation, from equation A and equation B, we conclude that equation 1 over here can be written as angle IBD is basically equal to half angle B plus half angle A. So let me call this equation as equation number 1, Roman number 1. Now consider angle BID. Angle BID is the external angle of triangle BAI. So angle BID is equal to angle IAB plus angle ABI. This comes from the property of an external triangle, external angle of a triangle. Further, we notice that angle IAB is half angle A. Same reason, I is incenter of the triangle and ray or segment AI bisects angle I, because I is the incenter. Further, angle ABI is equal to half ABI is equal to half angle B. Same reason, I is the incenter and BI is the bisector of angle B, because I is the incenter. So this equation over here, equation 2 becomes, using C and D, becomes angle BID is equal to half angle A plus half angle B. Let this be called equation Roman number 2. So what do we have here? Roman number 1 is equal to, the RHS is half A plus half B. Roman number 2, the RHS is half A plus half B. So the LHS of these two equations have to be equal. So angle IBD is equal to angle BID. So in triangle BDI, we have IBD is equal to this angle over here is equal to BID, this angle over here. So these two angles are equal is what we just proved. So in a triangle, if two angles are equal like this, then it becomes an isosceles triangle, and as a consequence we have BD equal to ID, or DB is equal to DI, what we wanted to show. So this is exactly what we intended to show. So BD is equal to ID is what we have proved here, which is exactly what we intended to show. DB is equal to DI. So the way we showed that DB is equal to DI, we can also show that DC is equal to DI in a similar manner, and this justifies the theorem that we proclaimed in the beginning, that there exists a circle with center D and passing through points B, I, C if you have a setting like this. I thank you for watching.